All right, in the mold chapter, we're going to teach you about stoichiometry. Stoichiometry is basically the ability to calculate ingredients or products, and really any occupation probably has that. So we're going to show you how the mole is something that we've been dealing with for several chapters now. We call it the coefficients in our balanced chemical equations. We're also going to tie it into molar mass and eventually get into some percentages towards the end of that chapter. So stoichiometry is a pretty tough spelling word, but that's about it. Stoichiometry really just means how much. So how much reactant do you need to make product? If you have so much reactant, how much product can you make? It's really no different than if you work at McDonald's and you're building a double cheeseburger. If you have so much bread, you can calculate how many double cheeseburgers you can make from that bread. Same kind of idea, if you had so many meat patties, then you can calculate how many double cheeseburgers you could make, assuming you have enough bread and so forth. So either way, if we're calculating ingredients to products or products to ingredients, it's just an answer of how much. And that's really what stoichiometry is. No different than a carpenter calculating how many 2x4s they're going to need to, frame a wall. So as we start to look at this idea of how much, think about conversions, because really that's where we're at in this part of the semester. So as we look at this example here, we notice very quickly that it says 5 eggs and 1 cheesecake. So if 1 cheesecake requires 5 eggs, how many eggs can make 2 cheesecakes? Well, really this 1 cheesecake to 5 eggs is just a ratio. No different than coefficients in a balanced chemical equation. So really what we have here is 5 eggs produces 1 cake, right? And now it starts to look like a balanced chemical equation where we have these numbers out front. So chemical reactions are really just recipes. They're just with fancier ingredients than sugar and vegetable oil and so forth. So if we know the ratio of reactants to products or ingredients to cake, we can calculate how much, and that's what stoichiometry really is. So if we want 2 cakes, recognize that we need to cancel cakes. So by putting cake on the bottom and by putting eggs on top, we can calculate, because these units cancel, that there's 1 cake per 5 eggs. So that just requires 10 eggs in the end. So again, this is not meant to be a difficult problem. It's just meant to show you that stoichiometry sounds fancy, but it's really just calculating how much. And that's what we're going to see a lot of in this next several chapters as we wrap up this semester. So the reason we saved chapter 2 for week 13 is to give you some early practice of conversions. This ability to cancel units down and across is exactly where we're at for the rest of the semester. There isn't many problems we're going to see that doesn't require some kind of unit cancellation through some kind of conversion factor. And what we're seeing in this previous example is that these numbers are just like coefficients. And we're going to call those moles in just a few slides. So let's expand on our recipe a little bit more. So we already know that there's 5 eggs. Next, it says that we have 1 cup of sugar. So 5 eggs plus 1 sugar. Now it really looks like a combination reaction because that still makes 1 cheesecake. So it really looks like you're marrying together eggs and sugar to make cake, just like we saw back in exam 4. So reality strikes and it says now we have 3 cups of sugar in the cupboard, no more, no less. How many cakes can we make without running to the store to get more? Assuming we have plenty of eggs to spare. So you can imagine that if this is 5 to 1 to 1, all we're really asking is, what if this is a 3? How does that ratio apply to the others? So many of you can probably do that in your head, and that's perfectly fine. The process that we're trying to get you used to is, if we have 3 cups of sugar, we want to get you comfortable with canceling units like sugar, but we'll call them moles pretty soon, and then getting cake, which will be product pretty soon. Then we're going to steal the numbers of 1 sugar per 1 cake, and that'll tell you that that's going to give you 3 cakes. So again, not meant to be difficult, just meant to show you that units cancel. And they have been for now 2 chapters in a row, and they'll continue to do so for 2 more chapters after this. So as we mentioned the mole, we talked about its SI unit for the amount of substance, and that's the case for this chapter. A mole to us is just a word like dozen. So when a baker says dozen, they mean 12. When we say mole, it's going to equal Avogadros number. It's going to equal grams on the periodic table. And it's going to mean a whole lot more in the next 2 chapters as well, with molarity and molar volume. So just think of mole as a dozen. It's a chemistry's dozen in this case, and our number is a whole lot bigger than 12. But this idea that mole is, some furry creature in biology is what you see a lot of cartoons in chemistry about. But really what we're after is looking at these numbers, recognizing that they are moles. So for example, as we look at this one here, we can say that 1 mole of hydrogen gas plus 1 mole of iodine can give you 2 moles of hydrogen iodide. So this idea of 1 to 1 to 2 now is just 1 mole to 1 mole to 2 moles in the end. So we can use moles for just about anything, whether it's coefficients, even the atoms. In H2, we can say that for every 1, so for every 1 hydrogen 2 molecule, there are 2 moles of hydrogen atoms. And no different over here, in 1 iodine molecule, there are 2 moles of iodine atoms. We could even look at HI and say, in 1 mole of HI, there's 1 mole of H atoms, and there's 1 mole of I atoms. So we can even use those subscripts as moles. So pretty much any number is fair game as a conversion to help us get what we want, and that's to calculate how much. Either how much, or in this case how many, atoms, or maybe how many moles of the ingredients can produce products and so forth. So our first definition that we're going to see on exam 5 regarding moles is Avogadros number. We typically use the 3 sig fig version, so 6.02 times 10 to the 23 is typically the definition that we use. And that's a huge number. So again, we saw this briefly with our intermolecular forces chapter. This is basically trillions upon trillions. And we said to get a grasp of this particular definition, this conversion factor, think of softballs. If we had Avogadros number of softballs, it could cover the entire planet. So a mole for everything is going to be different because moles based on the size of the atoms. So you might imagine that a mole of water is only 18 grams, but a mole of sugar might be, closer to 180 grams. So it really depends on how many atoms you have to how many you add up, and that's going to be our next definition of molar mass. So as we start looking at moles, just realize all numbers are fair game. If we want to compare atoms to moles, we can look at the subscripts. If we want to compare moles to moles, we can look at ingredient to ingredient or ingredient to product. Doesn't matter if we say moles or molecules. If we say molecules, we mean individual H2s. But as soon as we say mole, we mean 602 trillion H2 molecules, and that's a big difference. So molecule is the singular form, and mole of molecules would be the plural 602 trillion Avogadros number version of molecules. Big difference there. So as we start looking at these balanced chemical equations that we've seen as early as exam 4, we're going to see them again in this homework. But just know that they're giving you those numbers to give you a relationship in that recipe, in that reaction, to calculate how much ingredient is required to make product, or if we want so much product, how much of our ingredients are required. It's no different than if you find a new recipe, you might have to go to the store. And based on that recipe, you're going to calculate in your head how much you're going to need to purchase from the grocery store to make that cake or make that recipe. So our second definition of the mole is grams. And we've been cheating for a while mentioning grams, but it's only out of ease that we've done that. The reality of grams is you have to assume moles in order to get grams because atoms are so tiny. So our standard definition of mass is based on carbon-12. Carbon-12 is one of the most abundant atoms on the surface of our planet, so it's very easy to use that as a standard. And we know that carbon-12, being so common, weighs 12, and if we divide by 12, we get exactly 1 gram as a standard unit. The disadvantage of carbon, or any atom for that matter, is they're super tiny. So if we were to try to measure one atom, the disadvantage of that is, for carbon, it's 1.6 times 10 to the negative 24 grams. So just how many carbon atoms are going to be needed in order for us to recognize it on a balance? The balances that we use in the back of the classroom, they go to the milligram position. So that's 1 times 10 to the negative 3 grams. That's equal to 1 milligram. And those cost about $3,000 a piece. If you want to go to the negative 4 position, you're looking at about 10 grand for a balance that's capable of doing that efficiently. Even if we have that $10,000 balance, we need to go another 20 spaces further, smaller in this case, in order to measure one atom, and that's crazy. So if we can't measure singular atoms, how do we cheat and go away from AMUs that we've been technically using all semester long? We just assume a mole. If we assume a mole, that gets us back to our other definition of Avogadros number. And if we assume that we have 602 trillion carbon atoms, then and only then can we say there's 12 grams. Because you're looking at trillions upon trillions upon trillions upon trillions of carbon atoms in that little pile that makes 12 grams, or about 12 paper clips in mass on a balance. So as we look at molar mass, just think about adding up the numbers. These should be some of the easiest problems of this particular chapter. Just remember that when you're adding them up in grams, you're assuming Avogadros number of atoms or molecules are being counted. So it's not just one molecule, it's going to be 602 trillion molecules that you're going to be adding up when you add those bottom numbers in grams and not atomic mass units like we've been doing most of the semester. So really what we're seeing in this chapter is everything uses the mole definition. So we have lots of ways to do conversions. If we have moles, notice we can cancel them. So if we have some number of moles, we can cancel moles. But if we have some number of grams, we can cancel grams from the periodic table. If we have some number of particles, we can cancel with Avogadros number. If we have some number of moles, we can cancel with moles to get particles. So all of those are, reversible, flip side, upside down kind of ideas. We can use these conversions any way we want, as long as our units cancel. And that's the whole purpose of our previous chapter, is to get you used to canceling those units, whether they're moles or grams or now particles in the sense of Avogadros number. So let's try a practice problem. If you're looking at molar mass, as soon as you hear the word molar mass, you should think, go to the periodic table. When you look at gold on the periodic table, you're going to see that it weighs about 196.9665 and some change. And that's straight off the periodic table. Grams per mole is the periodic table, as long as we're assuming trillions upon trillions. How many moles of gold do you have? Well, then you take that number and you say, well, if I have 393.934 grams, I'm going to have to get rid of grams. And in order to get rid of grams, we're going to put it on the bottom. And that's exactly where that number from the periodic table goes. It goes right here. So we'll bring that down. 196.967, we'll say. And that's per 1 mole. And it turns out when you divide those, you get about 2. So we had about double. How many atoms do you have? Well, if you have 393.93 grams of gold, wouldn't that be nice? That'd be quite a lot of money. A lot of grams, I think, are $1,200 to $2,000 per gram of gold now. But again, cancel grams, go to moles. And then cancel moles and go to atoms. We only have 2 definitions. The only 2 definitions we have is find the periodic table grams if you assume 1 mole. And if you assume 1 mole, you're going to have Avogadros number of atoms. So it's at 6.02 times 10 to the power of 23. And this is where we'd use the periodic table, where it's about 196.97. So when you divide by 196.97 and you multiply by 6.02, you're going to hit the second next to the 1 button to get negative 23. And then you're going to hit equals. So it's going to be about 2 times Avogadros number. That's an important feature of Avogadros number. Notice those mole kinds of concepts. If we look at multiples of Avogadros number, we can see that 1 mole is 6.02 times 10 to the 23rd. We just see in this problem that 2 moles is 12 times 10 to the 23rd, or better said, 1.2 times 10 to the 24th by converting it into proper scientific notation just by moving that decimal over 1 more space. Then you can imagine as you get to 5 moles, some students get this confused. That would be 30 times 10 to the 23rd power, or just 3 times 10 to the 24th power. But a lot of students see 3 and they compare it to 6 and they say, well, that's just half of a mole when it's really 5 moles instead. So just be careful that you're paying attention to those exponents. These are very big positive exponents. And if you gain another power of 10, that makes a significant difference. So as we get into molar mass, we'll come back in a separate video to show you how to add atoms and grams from the periodic table, and then to use those further in conversions. Catch you then.